Hi guys, Mr. Johnny here. It's a lovely Sunday today, so I decided to spend some quality time trying to explain some stuff. Now, there are two approaches. I can approach this explanation from the rock bottom, but I don't like that approach for a few reasons. Namely, first of all, I don't have all that great of a knowledge to explain it from rock bottom. And another reason is, even if I know how it works and how to fix it, I just don't have the ability to explain it well enough for you to understand. So I will go with the second approach, which is I will rely on your knowledge, and I will explain it more in depth than I will explain it well, better than in previous video. But freaking bird. Yes, I am in rural area, you will hear that a lot. Freaking rooster always has to yell when I'm filming. Usually I film at night, so that's why you don't hear that. So, what a moron. Anyway, the mains come in through a forum fuse for a bridge there. This inrush limited resistor, which caused me trouble, that I replaced with a Soviet one, so it now works just fine. Comes in two these capacitors connected in series. There is this topology. This power supply is built by a topology called half bridge. One half of the bridge is made of MOSFETs, another half is made of these capacitors. There are two approaches to make this kind of a half bridge. You can use two electrolytics here, or you can use one electrolytic here. And when you use one electrolytic here, you will have two small film capacitors, just like this one, in same fashion as these two are. So you will have single capacitor here, and you will have just two film capacitors connected just like this across the rails. And then at the end of the transformer is gonna be connected to the joint of the two. I chose this one for a price reason, because it was cheaper to buy two of these capacitors for 170 microfarad 200 volts than it is to buy a single one which is rated for 170 microfarads or even 330 microfarads and 400 volts. So yeah. Then there are these two resistors which make sure that each capacitor is charged, has same voltage on it, has half of the voltage. That's supposed to be a divider. So, the chip used is a dumb chip. It's not a PWM chip, not a TL494 kind of stuff. It's not a PWM controller. This chip is really just an oscillator and a MOSFET driver. So, and yeah, about MOSFET driver, you may find it a bit interesting. The MOSFET driver, you may, I will rely on your knowledge that you already know how the MOSFET is usually driven. So I'm gonna go here and show you how the upper side MOSFET is driven here, because driving low side MOSFET is a piece of cake. Its source is sitting on the 0 volt rail, and it stays the same potential. You can discharge it very easy. High side MOSFET is a pain in the ass, because its source can be anything from the 0 volt rail up to your positive rail. So how do you do that? Is you employ bootstrap circuit, which looks something like this. That's your two MOSFETs in a half bridge. Primary, the transformer goes somewhere there. That's your bootstrap capacitor here. This capacitor. And the chip has a built-in diode. That's what the D stands for. There are some versions of this chip which is called like IR2153. And if you're using that kind of chip, you need to put the external diode between VCC and VB, which is bootstrap voltage. So how it works? When the chip starts up, it turns on this MOSFET first. So this is now connected to ground. This node is at ground potential right now. So the current from VCC flows like this, charges the capacitor. Then when this MOSFET is switched off, there is some time called dead time, and that is to prevent when the both MOSFETs are off, and that is to prevent cross-conduction. Cross-conduction is an event when the both of the MOSFETs are turned on, and effectively you put a huge load, if not a short circuit, across your rail. So I'm jumping all over the place. This capacitor is charged now. Then after that dead time, which is fixed, it is 1.2 microseconds here, if memory serves me right. The chip wants to turn on this MOSFET. You have this capacitor charged up here, one end of which is reference to the source of this MOSFET. So that's great. Now the internal driver inside the chip with these two MOSFETs, P channel and N channel. When the circuit wants to turn this MOSFET on, it turns on this transistor, which lets some of the charge to flow from this capacitor into the gate capacitance, and it will turn on the MOSFET. When you want to turn it off, the gate will discharge through this path. Easy. So that's how it works, how the high side MOSFET driver works here. Now, the dead time, as I mentioned previously, the waveforms are roughly look like this. Let's say that's a high side drive MOSFET, this one, and that's a low side MOSFET. When the first actually the low side MOSFET turns on, but let's start off with the top side, because I drew it this way. The top side high side switch turns on, then it turns off. And the low side MOSFET does not turn on immediately after this one is turned off. There is some time, as I mentioned, it's called dead time, 1.2 microseconds. Only after that time the low side MOSFET turns on, then it switches off, and then there is a dead time again, then the high side switch turns on again. In proper half-bridge drivers you will see that kind of dead time implementation one way or the other. It's a must if you use this topology. Yeah, some self-oscillating power supplies, half-bridge self-oscillating power supplies do not really have the dead time in it, but that's what causes them to fail sometimes and causes inefficiency and large idle current. That freaking bird. Anyway, so that's how it works. Now, I mentioned that this chip is very stupid. It's not a PWM controller. So how do I employ our current protection? Well, in the datasheet for this part, IR2153, I found a little schematic which showed that you can turn off this chip, shut it down, by pulling pin 3, which is timing capacitor pin, to ground, effectively shunting this capacitor over. That effectively halts oscillation and makes both output. This one will go to here, discharging this gate, and this MOSFET will be off, and the LO output is gonna go to the ground. So both MOSFETs are gonna be properly turned off. Excellent. They're not gonna be in chaotic state. That moron. They're not gonna be in chaotic state, they will be both properly switched off. That's what I want. So I put a transistor there. Next, I need some kind of control signal to control that transistor. I could have put a resistor, I can't put a resistor here because current here flows this way and this way. Yes, I could have implemented it, but it's a pain in the ass, so I decided to go with a current transformer, because it's easier this way. So we have a current transformer here, one turn here, just one turn through a toroid is when you pass the wire through the center of it once, and that's one turn. Okay. Secondary is 42 turns. The current transformer does not step down the voltage, it steps down the current. So let's say I have 1 amp flowing here, I'm gonna have 40 times less on the secondary. Then I feed that current into, I convert it to voltage by feeding it through a resistor, which creates a voltage drop across it. And if that voltage drop is big enough here, across this resistor, one end of which is on ground, where this emitter is, it turns on this transistor, yanks pin CT to ground, and halts the oscillation of the chip. Excellent. Now, a little bit about how did I calculate the current transformer. Current transformer is quite easy to calculate, actually. Let me write a couple of formulas so you'll understand what I'm saying better. So that's roughly how did I come up with calculated the current transformer. As I mentioned, it steps down the current, not the voltage. So I have base emitter, assumed base emitter junction drop of the transistor to 750 millivolts. Yes, it is smaller, but I knew I'm gonna put some resistors here, so it will drop a little bit. Oh, that feather moron. It yells like crazy. I'm gonna kick it with an axe a couple of times already. Freaking dumbass. Will you stop? Piece of crap. It's completely wasting my train of thought. So, I have base emitter voltage here. I have a desired primary current. How did I get this primary current? Well, I wanted 20 amps on the secondary. I know the turns ratio of the transformer, and I calculated the transformer using a software. I cheated. I did not calculate it full manually. I'm gonna show you that software in another video. Unfortunately, it is in Russian, so yeah. I may do a little kinda... I can't really modify it. There is no source code for it. And but I will make a picture where I will effectively translate all the text in that, so you can use that picture as a reference and use that software for yourself. Okay, so how did I calculate the transformer? I want 20 amps here, and what's the primary will be? Primary current. I know the turns ratio, and the transformer really looks like this. 34 turns primary, 5 turns secondary. Yes, it is 10 turns center tapped, but only 1/2 is active at a time. So, the primary current I calculated using this crude formula, which is not a preferred way to do it. There are some losses, there are some inefficiencies, makes life complicated. But the thing worked surprisingly well for this crude calculation. The first time I tried it, it was 18 amps instead of 20, which I calculated. But nothing is ideal here. Neither is this transformer, neither is this resistor or this transistor. Excellent result for this crude kind of stuff. Secondary current over turns ratio. So 20 amps, my desired secondary current. Primary turns, secondary turns. I came up with 2.94 amps. Then I plug this here. I rounded it up to 3 amps. And I wanted to use a 10 ohm shunt resistor. So then I need to calculate the current through that resistor to get me desired voltage drop. So it's VBE over shunt resistance, 750 millivolts across a 10 ohm resistor. That's a 75 milliamps. I do not really use standard units here, so you need to pay attention. That's millivolts over ohms is milliamps. pay attention. Secondary current of the current transformer is calculated using this formula: primary current times the turns ratio. I have one turn here in the primary, that's usually the case every time, and I want a secondary current of 75 milliamps, alright? Right here. So 75 milliamps equals 3 amps, my desired primary current, over turns ratio. 1 turn in the primary and x turns in the secondary. And that x equals to my secondary current over primary current, and you invert the result. That's why -1 is there, and you get 40 turns. So that's how I calculated it. But again, nothing is ideal. It was 18 amps, I wanted 20, closer to 20, so I put 2 additional turns here. Thus, I stepped the secondary current down a bit, and I still have the same threshold here when the circuit kicks in. So this way I moved the primary current up a notch. I hope that makes sense. Anyway, I managed to show you a little bit about current transformer, about the high side switch. Now I will try to quickly glance across what is this contraption for. One of my viewers, Cliff Matthews, I guess, yeah, if memory serves me right, sorry if I got it wrong, confused this contraption with a charge pump, and I see straight away why did he say that. That is because I drew it in a rather confusing way. This schematic is supposed to be for me, and I perfectly understand. Well, perfectly understand. Stop lying, you moron. I sometimes actually get confused with my own schematics and symbols, but that's a whole another story. Let's keep it short here. 17 minutes short. Anyway, so how this chip is usually powered? Usually, I mean in power supplies that other people make. This is not an entirely new idea, not entirely my idea. Quite a lot of people already use this kind of chip, this kind of schematic, this kind of circuit to make a power supply for a drill. What I did is I made it more efficient. I made this self-powering stuff which powers the chip, and I added over current protection so the thing does not afraid short circuits anymore. As you saw in previous video where that wire smoked pretty good and this thing just sort of survived just fine. Alright, so what is this for? Usually what other people do is they power the chip like this. Let's look right here. That's your chip, pin VCC, pin ground. There is a built-in Zener diode inside the chip. It is about 15 volts. And usually what the people do is they connect a big ass resistor, usually 27K 5-watt resistor, to a 325 volt line, which is this rectified mains right here, and the ground of the chip is right here. So what you have there is a dropper resistor. So the loss across that resistor is gonna be this voltage minus this voltage, which is 310 volts. You square that, you divide that by resistance of this dropper resistor, and you came up with a value with 3.5 volts. That's a lot. That will make that resistor smoking hot. Not only I do not have that value in this kind of power dissipation, having this kind of power dissipation in a fully almost airtight enclosure is not a good idea. Yeah. So I decided to kick it up a notch and use a trick which is usually implemented in a flyback power supplies, and that is a little bootstrap power supply. How it works is, luckily for me, this chip rocks a feature called micro power startup. What that means is that in order for the chip to start working, it needs just a little bit of current. The charge in this capacitor is perfectly enough to make the chip start to oscillate, produce waveforms, drive the MOSFETs and all the jazz. So how it works? You plug it in, there is rectified mains here, the current flows through these 100k resistors. There are 3 of them for power dissipation reasons. They are quarter watts each. Slowly charges this capacitor up to around 9 volts. Then the chip kicks in, drives the MOSFETs. Now you have the power on the transformer. Great. Then this winding takes over. There is voltage generated here. Then that voltage is fed into the circuit. That's a 12 volt zener here and 2 diodes and these components. Why are they here? Well, the voltage produced by this winding amplitude is much higher than I need It's much higher than 12 volts of this zener. So if I want to put these limiting components here, this zener will be fried pretty fast because it's a low impedance source. It will push quite a lot of current through the zener and make it die. So I could have just used the resistor, but that would have created a similar situation that it does here. Well, it ain't gonna generate 3.5 watts of heat, but still. So I decided, since I'm dealing with AC here, I decided to use a capacitor. So that's what this 22 nanofarad capacitor is for. This resistor is kinda like in rush limiting resistor. Honestly, I'm not sure if it's completely necessary here, but I put it in anyway. And why is it is only one half wave here, which is used to power the chip. And that is when this end is positive and when this end is negative. The current then flows like this. Through this diode, through the zener. Let's say there is no load. So all the current flows through the zener and back into the winding. If I wouldn't have this diode here, there would be no path for the current to flow when this end is positive. So when this end is positive, it wouldn't flow like this and discharge this capacitor. So that eventually this capacitor would be charged fully and won't conduct current anymore. That's why I have this diode here, to create a path for the other half cycle to flow through, like this, discharging this capacitor. Because you can make this circuit without this resistor, without this diode, excuse me, and you will see that this capacitor eventually will fully charge up and won't conduct current anymore. The circuit will crap out. Not the thing I want. This schematic is really simple. I decided to use it. I could have omitted this zener diode because, as I mentioned, the chip has built-in zener diode between pin VCC and ground. But that's the way I did it. I thought that it's a better idea. So that's that.